Good afternoon, everyone. I'm Eran, and I do work at Intel as a software engineer. Specifically, been working at the Advanced Analytics group for the past 7, and today I'm going to talk about how do you serve deep learning models in real time on top of video streams. So at Advanced Analytics at Intel, we develop, and deploy machine learning, artificial intelligence solutions across many Intel divisions, from sales and marketing through manufacturing and hardware validation. Some of our solutions even become products and are deployed outside of the company as well, such as several that we have in the health industry. We are composed of approximately 150 personnel, from machine learning engineers to data scientists and product managers, and mainly based at Israel. And today I want to talk about video analysis. A little bit of background: we have all seen how this subject of video analysis has been getting a lot of attention lately, mainly due to the improvements in the ability to process deep neural networks and a lot of research around neural networks, which helps us solve problems. And the question is, what kind of problems? Why do we need video analysis? Well, in general, the main problem everybody is trying to solve is video analysis for video understanding, in order to understand what we have in the video. And there are some core challenges in that field as well. And the main challenge currently, and they're always changing, is the segmentation of video or images, detection of skeletal movement of joints, detection and recognition of regions, such as we can see in the Simpson episodes, and even some advanced features from the past 2-3 years of the output of those networks would be a caption of the video or image that the user see. And since solving these core challenges will be very beneficial to a lot of use cases in the industry, such as autonomous cars, security, etc., there are also a lot of efforts in making those models lighter, compress them, prune them, so we can embed them and deploy them on edge devices in order to get fast inference. Our case was a little bit different, and our motivation was a little bit different. We were looking to automate visual inspections. We're actually approached by one of Intel's divisions, actually testing labs, in order to automate a process. Each one of Intel chipsets go through, after the manufacturing process, a testing process. And one of these tests are validations performed in labs, and the validation of live system outputs to detect if they have some kind of defects or anomaly in them. So this specific lab requested us that we would receive a feed of live video stream from them, where the camera would be positioned where a human would usually stand and identify whatever a human would usually identify, and made it a defect in this live system output or some anomaly in it. So after reviewing this special use case, we came to realize that we have a few more challenges on our hand, because we're looking at video analysis for visual inspections, which is a little bit different than video understanding. So first, the defects that a human may identify may come from very different worlds of knowledge, meaning we would probably, and this is actually what we saw in practice, need to deploy several deep learning models to, let's say, imitate one human vision. So that was an issue, because it added to our computational process. And another thing is, well, in video understanding, you can assume some kind of smoothness on the video, meaning if you want to identify what's in the video and the car is driving straight, in the next few milliseconds, it would probably still be a car. But so you can downscale your video a bit to reduce computational overhead. In our case, as we're expected to identify anomalies, every frame counts. There could be anomaly in those system outputs that are a length of a frame, let's say. So we needed to go through each frame in the video at 30 frames per second. As you can see, these are quite unique problems, and we're also expected to integrate into an existing process. We could not deploy our own equipment, but rather the lab would send the live video feeds to us so we can analyze it and identify those defects and anomalies. So after reviewing all these requirements and challenges, we have decided to develop a novel architecture that would centrally serve those deep learning models with focus on low latency. And I put emphasis on low latency because usually when you're talking about deep learning, a lot of people, or rightfully so, are talking about getting the highest throughput possible, because when you train, you want higher throughput. And sometimes, even when you serve, if you don't care about latency, you want the highest throughput possible. But we were requested to react in real time, or near real time, as a human would. So we needed the lowest latency possible. And not only the lowest latency possible for a single frame or a single image, but the lowest latency possible in a constant rate across the entire infinite video feeds sent to us. For instance, I wrote for instance. Yeah, for instance, if we have a few of those video cameras filming the process in the testing lab at approximately 100 frames per second, and this is actually a test that we did, each one of those frames would go to our main or single server in this picture, go through 3 convolutional neural networks, 2 LSTMs, and then there's a reasoning process taking all these results for each one of the frames, all these 5 results, assembling them for a final result, presenting it to the end user. And in this case, the end user gets that one of those frames was flagged as having a defect or an anomaly in it. We're able to do this specific use case, the entire processing in the middle, in less than a second, which is what we were expecting, or actually wanted to do. And we're able to do this fast because we are using the lowest possible inference time for each one of those models. As you will see, our architecture is designed to do exactly that. But this solution was not an easy one to develop, and we encountered some architectural challenges as well. And the first one, which is probably the hardest one to solve, serving CNNs or convolutional neural networks is a very heavily compute, time-consuming process, and just became part of our critical path, and we're expected for a fast turnaround to react in real time. So we needed to solve this. And if we were thinking about batching, because we know batching is really good no matter what hardware you're using, if you use batching, you get better vectorization, parallelization of the computations. So you want to batch. But if you batch naively, then while you're waiting for a batch to fill up, then your resources are idle and your latency will increase. So we needed to know how can we use this batching mechanism smarter in order to not increase our latency. As I mentioned before, there are also a variety of models, so we needed to do it for all the models in parallel and assemble the result in real time. And the last challenge was, as in any system, you want it to be scalable. So, okay, you can containerize it, you can put it on a cluster, you can deploy it, scale it. But the question here is when to scale, because if you're using the batching mechanism, which most of us do when we serve deep learning, while you're waiting for the batch to fill up, your resources are idle. And when you serve them, your resources may reach 100% utilization. So what criteria actually do you check to when to scale? So I'll take a sip of water before I continue, and we can deep dive into the architecture. So without any further ado, as they say, I present Archelon, which is how we call it internally. It's a scalable, fault-tolerant, and fully asynchronous serving system for video stream. And the asynchronous part usually comes as a surprise when you're talking about real time. But as you will see, this is actually helping us to reduce latency and get into the lower latency. In high level, the architecture is fairly simple. And we're going to deep dive into the important parts. And I'm not really going to talk a lot about technologies or go specifically into the code, but mainly the ideas, the concept, the principles that we used in order to help us serve video feeds that fast. So 4 main components. We got the API, the data store, the application, and the model. Down at the bottom, nothing fancy here, as they say, just frames going through the API, saved to the data store, Redis in our case, and result pulled from the data store through the API. The upper part is actually where the magic happens. We got the application part, which is, you can think about it as a collection of processes, asynchronous processes, as a matter of fact, which pulls frames and sets them for serving in the model part. And the model is a collection of microservices, which most of us use when we want to serve deep learning models. We pack each model as a microservice, and this separation of application and model is also very important for us to be more scalable. And as you can see, as you will see, it also helps us reduce the latency. I think the core of our architecture, something that is not, let's say, seen before, is the application part. So we're going to dive into that now. The application, as I mentioned, is simply a collection of asynchronous processes. This is our basic processing unit. We call them an AIU, or an asynchronous inference units. So this unit is always on, always looking to utilize resources, always working. It pulls frame from the data store, whatever it can find that's waiting for processing, pulls them, does some pre-processing, sends them for any model that it was configured to work with, in this case, TensorFlow serving model, let's say, gets the result from TensorFlow, understands them, does some post-processing, and saves them back to the data store. While it was working, some other frames arrived to the data store, so it just goes back to the data store, pulls whatever frames it has there now, and continue with that process. And as you can understand, continuous resource utilization. This also gets this kind of phenomenon of dynamic batching, because it pulls whatever it can find. But as you can see in this kind of architecture, the batch with quite fast will converge to this constant batch size that fits this model in the best way in order to get the lowest latency possible from that model. The AIU is also stateless, which means it doesn't have any state, stateless, and each state it needs, it saves and restores from the data store. This by nature makes it a very scalable and fault tolerant. Meaning, if you want to deploy more AIU to support this model, you can simply deploy another container or another one, and you will get a smaller batch size, maybe even increase your computational speed and lower your latency even more. Working this way has two more main benefits on top of the ones I just discussed. The first one is really good separation of concerns. Working this way, you can deploy an AIU for each one of your deep neural network. And each AIU will converge to the optimal batch size. For instance, you can deploy an AIU for your resonant model and an AIU for your object detection model. Since the models are microservices, it doesn't matter what framework they use. And the AIU for the resonant will converge, let's say, for a batch of 3 frames, and the AIU of the object detection batch of 2. And if, let's say, the AIU of the resonant needs help from a friend that will help them pre-process and post-process faster, you can simply deploy another AIU that will do the same thing for that resonant model. So first thing is separation of concerns. The second thing is, since the AIU is asynchronous and is also agnostic to which frames came from which streams, we can simply, if we use the same logic for all video streams, which we do because it's the same testing floor, then we can simply batch together frames. So it pulls frames, it doesn't matter where they came from, you batch them together, and then you get better resource utilization because you actually batch in order to reduce latency by batching multiple video feeds, frames that came from different video feeds rather. The question still remains when to scale. Now, while this question was a hard one to answer if you were batching naively when you were serving the models, it just became an easy one to solve with using the AIU because we have constant resource utilization. So instead of getting this fluctuation in CPU, GPU, TPU utilization, we have exhibit that most of our criteria converge into some constant range, mainly our batch size, our latency, and our resource utilization. So all that was left to do was decide, according to our operational need, when to scale. If we want to juice up our resources to get the lowest latency possible from a specific resource constellation, let's say, configuration, then we probably scale here. We'll add more resources because we're out of resources. But if we do care about really getting the lowest latency possible, then we probably need to set a threshold on latency. And once it passed that threshold, then we would probably or deploy more AIUs and see if it helps, or add another resource, computational resource such as CPU or GPU to our cluster. So that was the application. That was the core of our system. And the second thing I want to talk about what we did with the data store in order to enable us to work this way. So as a reminder, the data store is here in the middle. Gets frames, and the application pulls frames from that data store. It's a shared state, shared memory. We used Redis in order to implement this data store. And this data store, since everything else is asynchronous, we needed a place to synchronize things. And this is what actually enabled us to do the synchronization. We have written some kind of a queue management platform. Everything is a queue. The frames go into a queue. Let's say the frames are entities. Currently, the frames are going into a queue. And this is our input queue. The application pulls frames and saves those results into intermediate results queue. And then when this queue gets enough results, other process can pull them, assemble them, and save them into the final results queue. Now, as we can save frames, we also support ordered sequences as entities in those queues, meaning if we want to serve LSTMs, as we will soon see in the flow that I will present, we can pull from the data store ordered sequences in order to serve them to the LSTM, and not only single frames. So that was the data store. And the last part I want to go into is the model part. And serving models, I don't think that gets enough attention. Serving models in production and doing it fast is quite hard. And if you ask someone, and I can ask, but usually this doesn't work. If you ask someone, how do you serve your model in production, then the answer is usually, I'm using the framework that I trained it, and that's the way I serve it. And that's also the correct answer, because usually that will work best. But then it means that serving a TensorFlow model would require our AIU to have a dedicated client that knows how to speak protobufs and communicate with gRPC. And I was just saying that the decoupling of application and model is very important. So in order to do this separation, we've decided to develop a middle layer that we call the model service, that on the one side, it has a common API facing the AIU, and it only needs to know how to speak to it, asking it to serve a model, a specific model with those frames. It doesn't need to know what framework was used to serve that model. On the other side, this model service has a generic client that knows how to communicate with gRPC or HTTP, work with protobufs or multiple protocols. The AIU can consume it through Python package or as a microservice that mediates between the AIU and the model part. To conclude the architecture, I want to go through an entire data flow of the system. And this is actually similar to what we recently deployed in one of our labs. So let's say we have 3 models we need to serve, and then a reasoning process. So we deploy all the models, in this case using TensorFlow, LSTM, object detection, and ResNet. Then we spun up 3 containers, each one holding an AIU. And the first AIU is pulling sequences from the data store, pre-processing them, sending them for LSTM to get predictions, post-processing, and saving the final result to the data store. The second AIU does the same with single frames for object detection. The third AIU does the same for ResNet. Then there's the reasoning process, which is also an asynchronous process. The only thing that separates it from an AIU is that it does not do inference. It pulls all the results that it can find in this intermediate results queue that waiting for ensembling, and it finds that 3 frames, in this case, have 3 results from the 3 respective models. And let's say its reasoning is just doing OR between each one of the vector indexes. And it does an OR, and it finds out, well, there's 1 frame that was flagged as defected by one of the models, and I'm saving those final results to the data store for the end user to pull them from the data store and receive those findings. So that's the entire flow of the system. To conclude, I want to go through a bit more general suggestions on how to reduce latency. They are quite straightforward, but we found them very beneficial. The first one is receive a smaller image if it's possible, meaning all video cameras today, most of them send HD or even more resolution. Most deep learning models do not need high-def resolution images. I've seen up to 512 by 512 pixels. So if you can request smaller resolution, do so because it would reduce your processing time. If you cannot, then just resize it when you receive it on the spot before you save it to the data store, so you won't get stuck with a lot of memory going to waste and processing, of course. Second thing is separate the presentation and the prediction, meaning if you don't need the image in the process currently working, don't take the image with you everywhere because it will make you work slower. As soon as you can get rid of it, just keep it in the data store, do a computation, and attach the end result back to the image in the data store. I see you are agreeing with me, which is okay, which is good. Another thing is choose your processing resources according to your needs. GPUs don't work best for everything. They do work well. I work at Intel, if you don't know. And we have exhibited that some use cases, actually CPUs work better. Of course, for image, resizing the image, usually they work better. So test it. If it gives you lower latency, then use it. If not, try another resource, because specifically in TensorFlow, you can choose if you want to use TPU, CPU, GPU. Sometimes you'll be surprised. And the last thing, which also sounds trivial, use the best serving method for each one of your models, because this is the principle. If we're not serving the model itself the best way we can, that would not work. As you've seen, if you use TensorFlow, use TensorFlow serving much faster than building your own thing, loading your model, wrapping it with Flask, and trying to serve it. So these are general suggestions. And this was our architecture, specifically our AIUs, and some general suggestions. I was Eran, and I'm open to questions. I didn't hear.
Said, was the model always based on a single frame, or did you consider sequences of frames?
So what I said actually briefly is that it can be an entity in the data store, can be either a frame or an ordered sequence. So we handle that in the first saving mechanism to the data store. We save the frames as entities in the queue waiting to be processed, or we aggregate them and wait for an ordered sequence and save it as an entity according to size defined beforehand by, let's say, if the LSTM needs 16 frames or 10 frames, then we already they're ready as entities in the queue.
So the application is putting the predefined entities?
Yeah, yeah.
How do you manage to set back the result of the model to the application that puts the frames?
I'm not sure. I didn't understand.
How do you manage to get back the result to the application that sent the video stream? the Redis, about the API and then the Redis.
The API, since this is an asynchronous, the frames are saved through one thread and pulled from another. So according to the requirement, you can always build a layer that would synchronize this process. And let's say every few milliseconds would pull results and keep them. And when the user asks for them, it will give him what was just processed since he or she last requested the results.
How are you deciding the batch size, basically aggregation size for an entity?
The batch size, actually, this is the most exciting part here for me, actually, because we only care about getting the lowest latency possible. We just batch together whatever, the AAU just looks to the data store. Whatever is there, pulls it, and serve it. If it has one frame, it will serve one frame. If it has 10 frames, it will serve 10. If it has 1,000, it will serve a batch of 1,000. And what we've seen that in really a few of those operations, since everything else is constant, the model, the resources, and the throughput, then the batch size just converges to the optimal batch size in order to give you the lowest latency you can from that construction, from that actually, from those constant entities.
Why didn't you use any existing implementation of Q? Why did you go to your own implementation about Redis? Maybe Rabbit and Q or Kafka or something else?
That's a good question. I'm not sure I have an answer. We started using Redis. We didn't use queues from the get-go. We really liked Redis. And at first, you know how it goes. You think, well, we just need a simple queue. And we actually only use simple queues, so it was easy to implement. So we just implemented. And it worked well, so we didn't go someplace else, because the initial idea was we didn't think about using queues. It just came as we started working on it.
What did you use to do the modeling itself? Also, like Dockerized instances of like data science TensorFlow machines, or something else?
For the models,
Yeah, to develop the model to train and test.
we simply get from the data scientists exported models if we're talking about TensorFlow, or something else if we're talking about something else, because only TensorFlow has a really good convention for serving in production, and we wrap it in a container and we deploy it.
And data scientists use the same Redis store to look up the data, or they work
No.
separately,
They work separately on their own training data. It's good because I think I was fast. It's good that you have questions. How long did it take? It seems like 25 minutes. I don't know.
Yeah, you finished 5-10 minutes early.
Okay,
That's okay.
that's okay.
So we do have some extra time if anyone has any questions.
Any question? No.
maybe more about the backend side. So what do you need in terms of compute power for this solution, for the productionized version of this solution?
And this is actually really lightweight, because if you think about it, every component is really lightweight. Redis is in-memory, single thread. All of this can be deployed in one simple machine, like relatively simple with, let's say, Xeon in it, or one GPU, and it works. The overhead of our system, I didn't mention all that, but the overhead is really small. Is less than, I think, 5% computational power, and almost no consumption of memory but Redis. Because if you think about it, the real-time thing, we don't need the frames after we've served the results. So we don't keep them. They have a really fast timeout. We just throw them away. Everything is designed to get lowest latency, real-time. We don't care about history. We just care about what's happening in the last few seconds. More questions? Wait, I didn't. I was looking at him and hearing you.
Sorry, just say that again.
Okay, so do you still see some room for improvement? What would you like to do?
Oh, a lot of stuff. But my manager is also sitting here, so I cannot. No, I'm kidding. There are room for improvements, but I cannot detail them, I think, now.
What happens if one of these instances that are serving the model, if they crash, for instance, and they are processing one or a bunch of frames, what happens? They are given back to the Redis, they time out, and they are collected again for another second instance? What is
It's a good question. Everything is stateless, so it's really highly fault tolerant. But if frames were pooled and the AIU just during the processing part crashed, then it means that no results were saved for those frames. So if we spin up fast enough the AIU, then it will. So the frames will still be waiting for their processing because they did not receive results. Only when they get results, then we know we don't need to process them again. So that's one mechanism of reducing actually making it more fault tolerant. And that's I think the only point of failure that we can lose data. We actually had a big discussion if it's important or not, because if you're doing things in real time and maybe some small points in time don't matter that much, because this is simple. Our application we've written several, but mainly Python asynchronous processes written in Python. And each one of them is really lightweight. So if it falls a matter of milliseconds, you got another one up. Or we can even have redundancy of the processes, and it doesn't hurt us in matters of resources. They're not the bottleneck, so we can keep as many alive as we want.
During the presentation, you discussed about the scaling of the system. How do you manage to detect the increase of the latency in the processor?
So we keep we monitor certain criteria, mainly in this middle layer that synchronize the process. Like, when did I send the frame? When did I get the result for the frame? And we calculate these statistics, and we see those criteria that I said about the latency between the average time that it took between sending it and receiving the results. So this is the way. And then the batch size we can always see in the data store.
And then it triggers the spawn of a new Docker instance of some of the services.
What?
And then if the latency increases, it triggers the
Yeah.
spawn of a new
Either we spin up another Docker of an AIU that we see that's the heavily compute one, and or we simply add another or more resources to the system.
And you manage the resource weaknesses.
What?
How do you manage the resource weaknesses?
The resources?
Yeah. How are they managed with which tool?
This is out of my my expertise.
There was one final question. Okay.
In order for the AIU to know there are new objects to be processed, do you use Redis PubSub, or how do you know there are new things to be?
No, actually, it's a good. We tried to use PubSub, but we had issues because then you get duplicity of messages across AIUs. So we simply use the list and we do a pool from that list. And Redis works. I went to the Redis guy. It works so fast, then we didn't notice it did not increase our latency.
Okay. Then let's thank the speaker.
Thank you.